I'm going to start by warning you that this segment here is going to be notationally very heavy. Despite the fact that conceptually what we're doing is pretty easy, we've got this quadratic error surface that we want to minimize. We're going to move in the direction of steepest descent, a particular size, and we're going to do it over and over and over again until we get to a minimum. The derivation is a little heavy. And honestly, I could have just given you the answer here, but I want you to see the derivation, and particularly because I think it's important to derive these things from first principles. And later on, you'll thank me when we do neural nets, because it's important to understand how these optimization techniques work. So let me remind you where we left off. We've got our contour plot over here. The contours here, of course, are equal values of the underlying error. We've got some random point here. We're going to pick a direction that we want to move into, and then we're going to take some step until the error starts to increase, and we're going to do it again and again and again. And in the previous segment, we derived what the direction is. What we did is we computed the derivative of the surface, and we're going to move in the opposite direction of the derivative. That's going to tell me how to go downhill. So starting at u0, please move in the direction that decreases the error most quickly, which is the negative gradient. The gradient tells me the maximal increasing. I'm going to go in the negative. So remember that the derivative of the error surface at u0, my starting position, was equal to a u0 minus b. Remember that A and B have the data embedded in there. A was the x transpose x, and B was the x times the y, which are, of course, the underlying data. I'm going to move in the negative direction of that, which, of course, is just B minus A u0. So starting at some position u0, build the matrix A, build the vector B. Notice those aren't indexed. Those are constant. And then multiply u0 by A, B minus that. That will tell me the direction I want to go in. Good, that part is relatively easy and quite intuitive. You've got this parabolic surface, and you want to move in the steepest descent down. Think you're on your bike, and you want to go down that parabolic surface as fast as possible. You pick the direction of steepest descent. Now the interesting question is, well, how much? I mean, intuitively, we know exactly what to do. Keep going until you start to increase. So if you're on the bike, you go down, you start going uphill, well, stop. You stop right at the minimum. And then what do? Well, we're going to repeat the process, because now we're just at another point. We're going to pick the direction of steepest descent. We're going to go down until we hit a minimum, and then do it again, and then we'll eventually hit the minimum there. But now we need to know by how much. Okay, and this is the part that's going to get a little gnarly. Okay, negative gradient is the negative of the derivative, which is just b minus au. So let's formulate what we mean by move in the direction. I start at some position u0, and I want to move to a new position u1 right there by taking a step alpha, there it is, the step size, times the direction b minus au0. So there's my direction right there, b minus au0. How much? Alpha. And what is alpha again? It's when I take a step that is at the minimum along that single direction in this two-dimensional contour. So we know what the direction is. We know what we mean by move. We are going to add to the initial condition some amount of that vector. How much? Alpha. All right, that's the step size, and that's what we got to figure out next. All right, so let's see, how do I figure out alpha? Well, here's what I know. I know that the derivative at this point along that direction should be 0. That's what it means to have hit a minimum. So the derivative of E with respect to U1, sorry, the derivative of E at U1 with respect to alpha should be 0, because as I'm going along that direction, I should hit a minimum, and the minimum tells me that the derivative is 0. So this doesn't tell me what alpha is, but it gives me a constraint. So let's figure out what that derivative is. All right, so we've got the chain rule here. I've got my derivative of E with respect to U1, and I've got my derivative of U1 with respect to alpha. Well, this should be pretty easy to differentiate, so let's see what happens. Let's see, I've got a constant here. I've got alpha here being multiplied by this, and so the derivative of this is pretty straightforward. It's just B minus AU0. And of course, this is still the same derivative. All right, now, what do I know about these two things? They should be equal to 0. Why? because I'm going to drive down that one direction until I get to a minimum, which tells me that the derivative is 0. So notice that this product right here, what is this? B minus AU naught. That was my negative gradient, which is just dE of U naught, the initial step, du naught. So I can write this equation right here as this, and that's, of course, equal to 0. Okay, I haven't really gotten anywhere yet. In fact, it seems like I've lost where I wanted to be. Where did I want to be? I want to figure out what alpha is, right? But this equation doesn't explicitly have alpha. I mean, it's sort of in it here because U1 depends on alpha, but I haven't really gotten to where I want, which is tell me what alpha is. So what do I know at this point? Well, it seems like I've done a bunch of this derivatives, but I haven't gotten anywhere, but I have, as a matter of fact. And where have I gotten? I can tell you that the derivative at U1, the direction I should move into at U1, should be perpendicular to the direction at U0. And you may have noticed this, by the way, in all the graphs, is that those directions are always perpendicular. That's not an accident, and that's not specific to this plot. It is always the case, and here's why. Because when I hit a minimum going down this initial thing, the next direction, which will be the maximal descent down, is going to be perpendicular, and now we see why. I still haven't solved the problem that I want to solve, by the way, which is what is the step size starting at U1 and then, of course, at U0. But I now at least know something. I have a constraint. All right, now let's see how to use that constraint that the first two directions must be perpendicular to each other. All right, let's go back up to where we started. U1, my initial condition, my U1, after my first step, is going to be equal to U0, my initial point, plus alpha, that's the mysterious elusive alpha that we're trying to figure out, times the negative gradient, B minus AU naught. Let me define R sub 1 to be this residual that we call it, which is just B minus AUI. The reason I'm doing this is I'm going to use that R, I'm going to use this B minus AU sub I over and over again, and I just want to define it. So I'm going to define R sub I. Now, what did we decide on the previous slide? We decided that the derivative at U1 and U naught are going to be, the dot product of those is going to be equal to 0, which means that these two steps are going to be perpendicular to each other. Now, let's see if we can figure out what alpha is after all this. So I still have this question, okay, I know that the steps are perpendicular, but I don't know how much to take a step in. Now, let me rewrite this constraint as R1 transpose times R0. That's just the definition that I gave up top here. Okay, let me substitute back in what R1 is. What's R1? It's B minus AU1 transpose, of course, times R0 is equal to 0. Now, let's see. What do I want? I want alpha, this elusive alpha. Well, alpha, R0 is not going to help me, right? R0 doesn't have alpha in it, but U1 does because there it is right there. So let's break this out a little bit and see what's going to happen. So now I've got B minus A times U1. Well, what's U1? It's U naught plus alpha plus this term, which I'm going to use for R0 instead of lugging around that thing right there. Okay, so the good news is alpha has made an appearance. Here it is right here. And the other good news is I know B, I know A, those are my data matrices, and I know R0 because that's just this thing right here, which is the initial direction. And so it looks like we're starting to make some progress. And now we just need to do a little bit of algebra to factor out that alpha and solve for alpha once and for all. All right, let's do a little bit of algebra. B minus A times U naught, transpose, of course, because of that, times R0 is this term right here. And that has nothing to do with alpha, so I'm going to pull that aside. Alpha is going to be multiplied by minus A times R naught transpose times the R0 right there, and that's this term here. And now things are looking pretty good. This term is, of course, has nothing to do with alpha, and this term has something to do with alpha. So let's bring this over to the other side, and then we'll be able to take care of the rest of the term. So now what do I have? Let me put an R0 here first. B minus A U naught is R0, just to simplify that a little bit. And now let's go ahead and solve for alpha. Alpha, of course, is now equal to R0 naught transpose R0. That's on the numerator. And then I'm going to divide by this guy right here, which is the scalar value I have in the denominator. And finally, I've solved for alpha. Took a while to get there because we had to do those two steps. We had to first decide that the two directions that we're going to move into, sequential steps in the iterative least squares, are perpendicular. We use that as a constraint to then solve for the alpha, which we just did. So all of that was to come up with a very simple formulation, which is this iterative least squares works in the following way. You set up your quadratic error function. You pick a random value, u naught, and your direction is going to be the direction that is negative of the gradient at that point, which is just b minus a u sub I. How much do I move in that direction? I move in an amount alpha that I just calculated, where R1 with the Ri's, of course, are calculated up here. And then my new step is the previous step plus alpha times that direction right here. And now what's going to happen is I'm going to start at u naught. I'm going to move in some direction, which is determined by the negative gradient. I've just told you how much the step is. That's alpha. And then I repeat the process, repeat the process, repeat the process, and I eventually get, of course, to the minimum. That was a lot of algebra just to get to that very simple idea. If you didn't follow it entirely, it's okay. I suggest you go back and watch it, and there'll be some readings associated with this so you can follow it. And it's just a matter of cranking through the underlying algebra. What's important here, and by the way, we haven't seen where the savings is yet. We're going to do that, and we're going to implement this. But now we know what to do iterative least squares. Pick a random point in your space, pick a direction, the negative of the gradient. We know how much to move. Repeat, repeat, repeat until you get to the bottom. Now, is this more efficient? Is it any better? Is it any worse? Well, when we go to implement this, we'll see it, and we're going to see some variations on this to deal with some of the implementation details when we go to actually do this in the real world.